Okay, everyone, it's 10 past the hour and it's time for our final talk of the final workshop. So Nick, you're the big finale. So I'd like to welcome Nick Leaf. Nick's a dev tech engineer for HPC visualization at NVIDIA. And he's going to talk to us today about cinematic scientific visualization with ParaView and Omniverse. So Nick, let's see if you can share your screen. And you're muted, I think.
There we go. Can you hear me now?
Yep, perfect. Thanks.
Okay, lesson learned. Unmute myself before I share my screen. Okay, so hopefully I don't disappoint, being that I am the last person here, the last presentation. Hopefully we can go out on a high note. I'll do my best. So just to frame how I've been thinking about visualization a little bit lately, and how I think about it in the context of this talk. We cover visualization in a broad set of use cases. So there's a lot of very traditional ones. So like the upper right and lower left are kind of traditional volume renders. Upper right is an astrophysics data set. Lower right is scan data, microscopy data. And these are fairly large data sets. You'd like to explore them with high visual fidelity and interactively to really get at small details that may be buried within these very large data sets. And volume rendering is a great technique for that. We also have a lot of cases where we may have very complicated mesh data, such as the lower right case, which is a SpecFem data set. In that data set, advanced rendering, advanced lighting can really help tease out the structure of very complex surfaces without requiring quite as much time spent rotating around trying to notice little parallax differences. But we also feel like these sorts of 3D visualization techniques can expand beyond just those traditional use cases. So in the upper right, or sorry, the upper center is a database data set. What we did is we computed a 4D cluster on this. I think this is a database of Windows 10 errors, if I recall correctly. We computed a 4D clustering and then rendered that in ParaView with OptiX. The advanced lighting here helps bring out the structure of this data, whereas if all of these points were just flat shaded, they would probably just be basically a hairball. You wouldn't be able to make out any of these subtle details of shape in that particular center cluster. Adding a little bit of depth of field, adding some reflections can also help focus the data on what you want the viewer to focus on. But beyond just visualization, some of these technologies are also very useful for simulating in addition. So in the upper left, we have a sensor data set, and we're visualizing that using some ray tracing, but we could also simulate that. This is really important for instances of, say, like robotics, where you're trying to train in a virtual environment and you need to simulate LiDAR or radar sensors in as close to reality fidelity as you possibly can. That means you're going to be casting a lot of rays, and having accelerated ray tracing can really help that. So that's a lot of use cases. But none of these are strictly cinematic. So let me drive at what I mean by cinematic visualization a little bit more closely. So this is a COVID virus data set we got from the Gordon Bell winners from SC 2020. As we start out here, we're flying over a lung cell's lipid layer and then up the ACE2 binding site on that lung cell. And then we're now going over that infamous COVID spike protein that I'm sure we've all seen pictures of, and then flying over the lipid layer of the COVID virus itself. This whole data set is a few billion particles, but we were able to render it pretty comfortably on a single workstation. And that's partly due to the inherent scalability of the rendering technique. But to get this data into the renderer that we use, in this case was Omniverse Create, and I'll talk a little bit more about that later. To get that in, it really had to be a multi-tool effort. So we started loading the data in via VMD. We use VMD to pre-process, get the data into something we could load into Omniverse Create. We also use Blender to actually set up this camera path that we're following here. And all of that had to be brought together. One of the nice things about Omniverse Create is that it has that capability to work with multiple tools collaboratively so that you can pick the best tool for the job. You're not stuck in Omniverse once you get data in. One of the other big advantages is when you're working with Omniverse, the visualization that we're using for planning and previs before we render the final movie was pretty close to what you see here. We used a slightly different renderer, the RTX real-time renderer instead of the path tracing renderer, but it looks very similar. And that can help a great deal when you're trying to make these sort of cinematic high-end visualizations. If you know what you're getting before you have to send off that really expensive render, it helps a lot. So that when we did finally send off that final renderer and we rendered a ton of samples and we cranked up the resolution and added some expensive effects like depth of field and motion blur, we knew that we weren't going to end up just having to redo that 4 or 5 times until we tweaked the settings just right. So having these very high-end interactive tools, but making these high-end interactive tools work collaboratively and with very high performance can really help people create visualizations like this. And that's the whole goal, is to make visualizations like this easier for not just scientists, but for end users as well. So to frame that conversation, I'm sure I'm preaching to the choir here, but I just want to give some context to how I'm thinking about it. So you can think of these visualization tools as a sort of spectrum. On the far left is stuff that scientists are going to be using for themselves or to share data with colleagues on a daily or hourly basis. So things for like simple plots, even printf you could think of as a sort of visualization tool. On the far right are the more heavyweight tools that come from like the media and entertainment industry for creating film quality graphics like Houdini and Maya. Those tools are extremely capable. They're designed for really large data, so they can handle scientific data sets. But those tools are more or less a skill set in and of themselves. Often the creative artists that work with these tools spend a great deal of time mastering them and becoming really, really proficient with them. That's not something that most scientists necessarily want to take the time to do. They might rather be doing research than learning how to use Houdini in excruciating detail. But we'd love scientists to be able to create those level of graphics for themselves. It's useful for outreach to the public. It's useful for help explaining what they do and teaching people about what they do. But I think it goes beyond that. I mean, it would be nice to have those sorts of high fidelity visuals in everyday practice. So I'm not claiming we're there, not by any stretch, but it's something that we're continually working on and continually working towards, is kind of squashing this spectrum, bringing these two ends closer together. So I alluded to the fact that I don't see these high-end graphics as just something for outreach, like, oh yeah, you do all of your science and then like a year later after you get your interesting result, then you make a video for a conference. And I just want to show this picture quick to help drive that point home. So on the left, you have a more traditional volume rendering, and on the right is something with RTX on. So that's got a few more bounces, multiple scattering, and some ambient occlusion. And using the visualization on the left, you can certainly draw some details out of that. You could mess with the transfer function, and a proficient scientist or visualization expert could certainly tease out all of the structure that's visible on the right. But with the picture on the right, you don't have to do that. It's just there. So that's great for the public. These look more like normal clouds. The public can more easily understand what they're seeing here. It matches up with their expectation of reality. But I argue it's good for the scientists too, as long as they don't have to put a ton of extra time into making that happen. So towards that end, we've done some work in the past to work with collaborate with Kitware and get some of our rendering technologies directly into ParaView, where scientists and viz experts can access it. So on the left is a picture from our OptiX path tracing backend. This is available starting in ParaView 5.8, so it's been out for a little while now. As long as you have an NVIDIA GPU and a reasonably recent installation in ParaView, you can just turn this on and immediately get physically based lighting, good shadows, ambient occlusion, reflection, all of the sorts of details you'd expect to get from a path trace renderer. On the right is a picture of the NVIDIA Index plugin. Index is a great tool for rendering really, really huge volumes. It's inherently multi-node, multi-GPU. It's got a very fast, unstructured mesh sampler, and it also produces some really beautiful images. So those are both available today. We wanted to take it yet another step further. So we've been looking at trying to make visualization easier inside basically where scientists already live. Not every scientist is out there using ParaView on a daily basis. A lot of people are using Jupyter on a daily basis. That's their main tool, their main IDE and analysis environment. So we tried to bring some of these technologies to them as well. We created a pretty simple widget called ParaView that just lets you natively run ParaView Python inside a Jupyter notebook. So the little example I'm showing on the left is just a CT skull data set. I computed an isosurface from it. The data set was loaded in Python. I sent it over to VTK. I computed the contour filter from that. And then using IPy widgets, wrote a couple of little simple controls and made like a simple lighting UI along with the interactive visualization window. So the point is, it's all configurable. It's all working in an environment that scientists are already somewhat comfortable with, and it allows them to visualize directly in that environment without having to save data to disk and then load it up in some different interface. Another project we've been working on at NVIDIA is called Node Rapids, and that's designed for GPU accelerated JavaScript rendering, in particular, using the rendering capabilities on a server, on the Jupyter server, rather than relying purely on the client. This fits a lot of use cases in, scientists are often running on a notebook or something really lightweight that may not have all of the rendering horsepower they would like, and yet they're connected to some really high-end server with a ton of horsepower. So rather than force them to download their entire data set to the client browser and render it there, it'd be nice if they could just render and stream on the server. And that's what the Node Rapids project is intended for. So I dropped a couple of links to GTC talks and GitHub repos if you're interested in that. But I alluded to earlier that we use Omniverse for that COVID visualization I showed a bit ago. And I mentioned that we use multiple tools. And that has been a problem that we've noticed in a lot of different industries. So media and entertainment certainly suffers from this problem, where artists are using a ton of different tools and all using tons of different workflows and different file formats, yet they all need to collaborate together and ultimately bring all of that data somehow into the same place so they can actually render their real output. And usually this means users are managing file formats and file versioning themselves. And then you have to have people who are not just experts at particular tools, but people who are experts at interoperability between these tools, maybe on even just like a pairwise basis. And then into this mix, because it's not complicated enough, we wanted to make ParaView work with all these other tools as well and bring everything together. So not just, okay, you can get data from ParaView into these other tools, but you'd like to take your data from ParaView and combine it with the output of all these other tools to help make visualizations higher fidelity, make them more cinematic. So to make this work, we could make ParaView individually compatible with all of these. That quickly becomes an n-squared problem if you're trying to maintain pairwise compatibility, and it's just not sustainable. So you need some sort of common format that all of these tools are comfortable working with. The universal scene description format was originally created by Pixar for their own internal use, but they've since open sourced it. And it's gained a lot of traction throughout from a number of big players, NVIDIA included certainly, but also Adobe, Apple have made big bets on USD. So it's rapidly becoming a common denominator format, or as the tagline I have on here, it says the HTML of 3D worlds. It allows heterogeneous data, so you can have meshes, you can have points, you can also combine that with everything else you might need for rendering material assignments, lighting, and so on. So anything that speaks USD can easily talk to anything else that speaks USD, and that's a great first step. But with the pain points I mentioned earlier, managing file formats, managing file versioning, and working remotely on the same data sets, that gets rid of the file format problem. There's still those other two. Even if everything speaks USD, users still have to worry about versioning and trying to email links to files back and forth. All of that is a lot of overhead, it's tedious, and it's a drag on any sort of creative process, whether that's creating high-end graphics for films or creating beautiful scientific visualizations. So to go that next step further, we've created something called Omniverse, and the core of Omniverse, the Nucleus server, that lets applications connect directly to a Nucleus server instance and incrementally update USD files, so that somebody changing a texture in Photoshop and somebody else changing some scene geometry in a DCC tool can combine all those results in, say, Unreal Engine, and someone else can explore those results live as the other two are working on it without anyone having to email a link to a file back and forth. So the name Omniverse hints at a little bit more than just a USD database, though. And it encompasses a pretty broad range of technology. So you can see I have Nucleus server on here, and that's definitely a core part of Omniverse. We also consider all the connectors a part of Omniverse. And what I mean by a connector is even something as simple as just being able to import or export USD. So if something can write a USD file or read a USD file, that can be said to connect to the rest of Omniverse. But in a lot of cases, these tools can actually go a step further than just writing or reading file systems. They can connect directly to Nucleus. They can do incremental live updates to USD files. And that lets them get this sort of simultaneous remote collaboration that we think really speeds up workflows of all sorts. ParaView is in that latter category of sort of heavily connected to Nucleus via the ParaView Omniverse Connector. And I'll talk a little bit more about that, I think, on the next slide. So what else do you get from Omniverse other than just that database? You get access to an RTX renderer. So this is a very high-end ray tracing renderer, both a real-time version that's focused mostly on speed and a path tracing version that is focused more on quality, but is still really quite fast. And then both of these rely on the MDL open source material definition language. One of the big advantages of this for scientific workflows is that scientists hopefully don't have to, and really, in my opinion, shouldn't have to learn how to master all of these creative tools to be able to get something that's film quality rendering. So if they don't have to learn how to create a material, they can just drag and drop from existing material libraries. They can get that high fidelity viz without having to spend a ton of effort. What I hate to see is for them to have some sort of beautiful simulation data, and then maybe they put in some context objects, like if they're simulating airflow through, say, a data center, if all of the data center's objects, if all the racks are just flat shaded and not metallic, well, that detracts a little bit from the overall visualization, and that can distract particularly lay people from the takeaway message. because they may see this beautiful visualization and this really high resolution data juxtaposed with a crappy looking flat shaded rack that just looks like a box from the, like a portion of the Cornell box from the 90s. So materials can help with that. We also have included some simulation capabilities. So this would be physics, real-time physics using the NVIDIA physics library or NVIDIA Flow for real-time CFD. And we also have some AI built in and a couple other things. So physics come in not as a replacement for any high-end accuracy-focused physical simulation software or code, but they come in more as an exploratory tool. So for instance, you could get a mesh into Omniverse and do some exploratory flow viz using this real-time package and play with that interactively, help understand what your initial flow might look like before you set up your simulation parameters. This can also be used to great effect to explore existing simulation data. So if you have a CFD simulation and you have a velocity field from it, you could import that to Omniverse and use NVIDIA Flow to advect smoke through that flow field. And that sort of exploratory smoke viz is something that is really intuitive to lay people, but it also can be really expressive for experts as well. It gives them a lot of control to test out and see how their own flow field works. Both of those render and simulation capabilities, as well as the ability to connect and live sync to Nucleus, all kind of come together in the Kit SDK. The Kit SDK is just a framework for building applications, so most people will interact with it through one of the Omniverse apps, usually Omniverse Create or maybe Omniverse View. But Omniverse Create is a little bit more full-featured. It's meant to be both a live viewer and editor so that you can jump in and view these USD scenes as other people might be changing them, as well as make some modifications yourself. So the best comparison for Omniverse Create would be something like Blender or Maya, something that's a full-featured DCC. It's not a strict replacement for those, but it does add some other capabilities as well. So the way that ParaView connects into this whole ecosystem is via the ParaView Omniverse Connector. How that works under the hood is it will take a renderable representation. So this would be something after you've already run some initial pipeline to get the representation you're interested in. So maybe you load up a volume data set and use a contour filter to compute an isosurface of that. That isosurface mesh would then be the renderable part of the data. That may include also a color map that maps to an important data quantity. That renderable data will go into the ParaView Omniverse Connector, where it gets converted into USD data. And then that USD data could just go out to your local file system if that's what you want, or you could also connect directly to a Nucleus server and output that data directly. The really exciting part of that connection to Nucleus is if you have one person working in Omniverse using like Omniverse Create and another person working in ParaView, that person working in ParaView can tweak the pipeline and work with it to get exactly the visual representation they want, while the person in Omniverse is working on setting up, say, context objects or creating final renders. And all of that can happen simultaneously and collaboratively without having to send a single email back and forth. The ParaView Omniverse Connector works with a lot of ParaView's capabilities already, so it can be run in headless mode. So you can do offline transformations from whatever data set ParaView can read into USD, but it also can work with ParaView's multi-node capability. So it's pretty ParaView centric. I think any ParaView user will be comfortable with that sort of workflow, and it's an easy gateway to get data into Omniverse from wherever you have it. So to show how this works with an example, I'm using a fuel injection simulation courtesy of Christoph Garth here. I already have the Omniverse Connector plugin loaded. And here I'm just setting up a couple of precursors. So I have to select a particular nucleus server that I'm interested in, or whether I want to output to local disk. In this case, I'm using a nucleus server. Once I have that, all I have to do is create a new layout and create an Omniverse Connector view. The connector under the hood will use that view to scrape all of that renderable representation data directly from ParaView before transforming it to USD. So once I have this view, I just have to enable the pipeline object I care about, which is the stream tubes at the end of my pipeline. And all of that data will automatically be sent over to Omniverse. So this is Omniverse Create, and that's the exact same data set I was working with just a second ago in ParaView. Editing this in real time, you can see I'm selecting an object and I'm messing with some material properties. All of that can be done in real time. I can change reflectivity, metallicity, I can change the roughness of surfaces, everything you expect to be able to get the look exactly what you want. But you notice that even with this super complex flow field, with a lot of turbulence and a lot of overlapping stream tubes, I'm able to distinguish those features pretty easily. And that's all comes naturally with the advanced lighting and proper shadowing and the like. So I switched over to the path trace renderer and I cranked up the number of samples to kind of really get the maximum possible quality. But even though I'm using the path trace renderer, you can see that it's pretty quick. I can still interact with it, and it's really not painful to do. There's some denoising built in there, obviously, that helps that, but it's a really nice tool to work with to set up that final render and get that super high quality renderer. So this is a nice example of taking some static data and getting that into Omniverse and creating a nice image. But where we'd like to go in the future is enabling even a tighter coupling and a full end-to-end pipeline. So this is an example we showed a while ago, I think from GTC 2019, and this was all very prototype at the time. This couples SimNet, which is a DL-based physical simulation package, with NVIDIA Omniverse. So SimNet is used to compute this flow field as the design parameters of these cooling fins are changed. So the designer is working with this interactively and changing these parameters and then seeing the result of their parameter changes in real time. So they don't have to change a parameter, run a simulation, send the simulation off for viz, get the result back. They just change it and see the result. And that can greatly speed up workflows. To actually visualize this flow field, in this case, we're using that flow CFD package I mentioned. So the flow field itself is input from SimNet, and that smoke that you're seeing in the viz is advected through the flow field in real time. And then all of that's visualized in Omniverse directly. So that's about what I wanted to cover today. If any of this is interesting to you, and hopefully if I've done my job, some of it at least piques your interest, this is all available now. Omniverse is available in beta. You do have to sign up for it, but once you do, you can download the launcher, and the launcher gives you access to all of the rest of Omniverse. The ParaView connector works with ParaView 5.9 or newer, and all you have to do is to get that is have the launcher downloaded and download the ParaView connector from the launcher, and that'll walk you through the steps to get that installed. Once that's installed, then you can just follow the steps I showed a little bit earlier to get data from ParaView and Omniverse. And right now, that's probably the easiest way to get data into Omniverse, since ParaView has such a broad range of capabilities and readers. I also left a couple of links here to a GTC 21 session that I did that covers some of this stuff in a little bit more detail. I mentioned that ParaView is one of the best ways to get data into Omniverse right now. It's not the only way. You can work directly with USD. USD is a pretty nice format. I've done some direct to USD stuff myself from Python using USD's Python bindings. So I left a link to a session introducing USD if you want to explore that more. And with that, I am all done. And so I'm happy to take questions if you have them.
That's great. Thanks very much, Nick. Let me just open up the Q&A. So there's a question here. When it comes to the nucleus and the central Omniverse parts, are they hosted by the user? So the question is, do you have to host them yourselves, or is there a cloud-hosted solution from NVIDIA?
You know, that's a great question. Right now, I think we focused on letting people host their own nucleus servers with the idea that there are a lot of users that don't really want their data going off premises. So I don't know if we're offering hosting services ourselves yet. With that said, you can also just spin up a nucleus server pretty easily through the launcher. You can download your own nucleus server, run it locally, connect to your own local nucleus server, and then you could also have collaborators connect to a nucleus server that's just running on your machine. So it's not too painful.
Okay, I have a question. Some of the talks today have touched on having so much data that we can't rely on it being on disk. So with the ParaView connector, is that something that would that work with in situ visualization, feeding it out to Omniverse, or is it intended at the moment for data you have on disk?
So right now, it is intended to work with data that you have in ParaView. So I don't think it would work in situ. I would love for that to happen. I think that should absolutely be one of our next steps. But right now, it requires a spun up ParaView, basically a ParaView render view or something like that. And so I don't think that is available through Catalyst right now. But in the future, I'd love for that workflow to be possible.
So it's interesting. I work in fluid dynamics myself, and I saw the stream tubes you had in ParaView, and I thought, oh, they look, that's what I'm used to. And then you open it up in Omniverse with the rendering there, and it is interesting the added dimension that brings.
Absolutely, and that's part of the trouble too, is that workflow has been possible for a while, but it's not easy enough. I'm not going to expect a lot of even Viz practitioners to go learn some of these high-end tools and get all of their data, transferred back and forth on a frequent basis. That's going to be an infrequent thing. So I maybe left the ParaView side rendering in its initial state just to really kind of, I guess for marketing purposes, to kind of enhance the transition to Omniverse. And Omniverse does have a good renderer, but even using the OptiX path tracing and backend in ParaView will give you those sorts of great visuals. Well, just using path tracing in ParaView will give those sorts of great visuals. I just I have to cheerlead the NVIDIA approach a little bit.
Sure. Yeah, Garth.
Thanks very much, Nick. I mean, there were some great images there. Just a kind of question or a comment to begin with, maybe. I know I've been trying for a long time to get some even just basic visualization to work in Jupyter notebooks, and it's just been such a moving target over the past 5 years. And at the moment, because Jupyter Lab keeps changing, the extensions keep breaking. I mean, is there hope that at some point we can do reliable 3D visualization in a notebook and have it work for more than a week?
I mean, there's definitely hope, and I think that definitely should happen. But like you said, the foundations are changing under our feet a little bit, so it can be a bit of a moving target. To my knowledge, IPy ParaView has been relatively stable so far. It's not as easy of a workflow to install as it could be or as it should be, but it has been worked across quite a few different versions of Jupyter Labs. I know there's some other great 3D Viz packages that also have a fair bit of support too.
Yeah, no, I'm really keen that we can do more with it, and hopefully it settles down. But I think with Jupyter to Jupyter Lab, we've just found the dependencies haven't been keeping up in the last year or so.
Yeah, well, I think part of it is this dichotomy between client-side rendering and server-side rendering. There are quite a few client-side rendering packages, but my reluctance with client-side rendering is the problem where people have thin clients, but also the fact that things do keep changing on the client side. Whereas if you have server-side rendering, as long as you can make that streaming sort of approach fairly painless, your client-side dependencies should be kind of light and hopefully a little bit more robust to changing interfaces. So I'm bought into server-side rendering, and what I particularly like to see is us enable Omniverse in Jupyter. It's a little ways off yet, so I don't have a timeline for that, but my personal wish is to be able to do Omniverse directly in Jupyter and have that stream, and that should be hopefully maintainable and still give you great results.
Okay, thanks.
This may be a related question. So the question is, so you spin up an NVIDIA Nucleus on a remote system which has RTX cards, and then you go ahead and connect to it remotely and use those remote cards to do the rendering, server-side rendering. So that's just is that how we're expected to one way that you could run NVIDIA Nucleus remotely?
Yeah, so that is definitely one way. So that would be in that case you'd be running Omniverse Create and you'd be streaming locally. And so we do have some streaming capabilities already built in. How I usually run it is I usually run on a workstation, but I happen to have a workstation with beefy NVIDIA cards sitting right next to me. But both workflows will function just fine though, and they're both good options. I really like that server side heavy end GPU, especially because it'll let people both work on whatever device they're comfortable with and utilize some existing institutional resources that they might have.
Okay, thanks, Nick.